Every public API on the internet has a rate limit. Twitter limits you to 1,500 tweets per 15 minutes. GitHub limits API calls to 5,000 per hour. Stripe limits their API to 100 requests per second. Without rate limits, a single misbehaving client or a malicious attacker could bring down your entire service by flooding it with requests. Rate limiting is your first line of defense, and the component that sits in front of your services to enforce these limits, along with authentication, routing, and many other cross-cutting concerns, is the API gateway. In this final fundamentals video, we'll cover rate-limiting algorithms, where to implement them, and the role of the API gateway in modern system design. This is also one of those topics that rewards specificity in interviews. Knowing there's a thing called token bucket is table stakes. Being able to explain why it's preferred over fixed window and how you'd implement it at scale with Redis is what earns the higher signal. There are several algorithms for implementing rate limiting. Each has different properties in terms of smoothness, burst tolerance, and implementation complexity. Token bucket is the most commonly used algorithm. It allows users to occasionally burst above their average rate up to the bucket size, which is important for real-world clients that legitimately have spiky usage. A user who's been idle for 10 seconds has 100 tokens accumulated and can burst at that rate. The implementation is elegantly simple. For each user, store two values, the token count and the timestamp of the last request. On each request, compute how many tokens have refilled since the last request, rate X elapsed time, cap the bucket at its maximum size, subtract one token, and check if the result is non-negative. 2 fields in Redis is all it takes. This simplicity is why Token Bucket is the industry standard. AWS API Gateway, AWS Lambda, Shopify, and most cloud-native rate limiters use Token Bucket. When an interviewer asks, which algorithm would you use? Token Bucket is the correct answer for general-purpose rate limiting, and you should be able to justify it in terms of burst tolerance and implementation simplicity. The fixed window boundary bug is worth understanding precisely. If your limit is 100 requests per minute, a client could send 100 requests in the last second of minute 1 and 100 more in the first second of minute 2. 200 requests in a 2-second window, despite the 100-minute limit. For most APIs, this is acceptable. For sensitive endpoints like login or payment, it's not. The sliding window counter is a practical compromise. You store 2 fixed window counts, the current window and the previous, and compute a weighted interpolation count. Previous window count X, 1, elapsed window.size plus current window.count. This eliminates the boundary spike with minimal additional memory. Redis sorted sets can implement the sliding window log, 1 entry per request, keyed by timestamp. Though at high request rates, the memory cost grows linearly with request count. Rate limiting can be implemented at different points in your architecture. The most common place is the API gateway or a dedicated rate limiting middleware. This centralizes the logic and handles all services uniformly. The rate limit counters need to be stored somewhere shared, usually Redis, so that all instances of the gateway see the same counts. Without this, a user could spread their requests across multiple gateway instances and bypass the per-instance limits. In distributed systems, you might also implement service-level rate limits. For example, the payment service limits how many payment attempts it accepts per user per hour, regardless of the API gateway rules. The Redis implementation pattern for Token Bucket is worth knowing in detail. On each request, run a Lua script executed atomically by Redis that fetches the stored token count and last refilled timestamp for the user key, computes tokens to add based on elapsed time, caps at bucket size, decrements by 1, stores the updated values with a TTL equal to the window size, and returns allow or deny. The atomic Lua execution ensures no race condition between the fetch and the write, even under high concurrency. This approach handles 100,000 plus rate limit checks per second on a single Redis instance, which is why it's the industry standard for distributed rate limiting. For higher scale, you can use Redis cluster, sharding the rate limit key space across multiple Redis nodes. Each user's key lands on one node. The lookup is always local to that shard. This scales to millions of rate limit checks per second, linearly with shard count. The API gateway is where you centralize all the logic that every service needs, but none of them should implement themselves. Without an API gateway, every service needs to implement authentication, check API keys, validate JWTs, enforce rate limits, and log requests. You'd be duplicating this logic across dozens of services. With an API gateway, each request is authenticated and rate limited once at the entry point. Downstream services can trust that any request reaching them is already validated. The API gateway also solves the client interface problem. Mobile clients, web clients, and third-party partners all have different needs. The gateway can aggregate multiple service calls into a single client-facing response. The back-end for front-end pattern handle API versioning so you can evolve your internal services without breaking external clients and transform request-response formats. In microservices architectures, the gateway absorbs the complexity of service discovery. The client doesn't need to know that orders routes to the order service and payments to the payment service. The gateway handles routing transparently. When you're asked to design a system in an interview, rate limiting is a detail that interviewers love to ask about. Here's a concise answer structure. At the API gateway, use Redis to store sliding window counters keyed by user ID or IP. Token bucket for general API limits, stricter limits on expensive operations, search, file upload, authentication attempts. Return 429. Too many requests with a retry-after header, so clients know when to try again. For your most sensitive endpoints, login, password reset, payment, implement both rate limiting and exponential backoff on the client side. While we're talking about protecting services, circuit breakers are worth mentioning here. Rather than rate limiting inbound requests, circuit breakers limit outbound calls to struggling services. If the payment service is returning errors 50% of the time, your circuit breaker opens and you return a cached response or a graceful error, rather than continuing to hammer a service that's already struggling. Every public API you design needs rate limiting. Say it without being asked. This signals production maturity. Here is the complete framework. State the requirement. Any public-facing API endpoint needs protection from both malicious abuse and accidental overload. Rate limiting is mandatory. Choose the algorithm. Token bucket for general API limits. It's standard, allows burst tolerance for legitimate clients, and is trivially implemented in Redis. Fixed window if simplicity is required, and boundary exploits are acceptable. Sliding window for sensitive endpoints, where the boundary bug is unacceptable. State the implementation. Redis with atomic Lua scripts. Key the counter by user ID for authenticated endpoints. IP address for unauthenticated ones. Set a TTL equal to the window size so keys expire automatically. This handles 100K plus checks per second on a single Redis instance. State the response. Return HTTP 429 too many requests with a retry-after header and rate limit metadata in response headers: X rate limit limit, X rate limit remaining, X rate limit reset. This is what clients need to back off gracefully. Mention tiered limits. Different rate limits for different client tiers. Free tier gets 100 requests per minute. Paid tier gets 1,000. Partners get 10,000. The API key determines the bucket size and refill rate. The API gateway handles all of this centrally. Authentication, rate limiting, routing, SSL termination, all at the gateway layer. Downstream services receive only validated rate-limited requests and implement none of this themselves. If the interviewer probes on DDoS specifically, rate limiting by IP at the gateway is your first line of defense. Cloud providers, AWS Shield, Cloudflare, absorb volumetric attacks at the network edge before they reach your gateway. A well-architected system has both. These numbers let you make specific claims in interviews rather than vague generalities. LinkedIn uses token bucket rate limiting and limits developer applications to 1,000 API calls per day for the default tier. Per endpoint limits are stricter. The profile endpoint is 100 calls per day for free tier apps. Twitter's V2 API limits reads to 300 requests per 15-minute window for app-level access, 20 requests per minute. Write endpoints are stricter, 300 tweets per 3 hours. Stripe's API limit is 100 read requests per second and 100 write requests per second in live mode per secret key. Stripe uses token bucket and returns a 429 with a retry-after header on limit breach. Redis can handle 100,000 to 200,000 rate limit check and increment operations per second on a single node using the Lua atomic script pattern. For most systems, a single Redis instance is sufficient for rate-limiting storage. A Redis INCR plus EXPIRE pair, the simplest fixed-window implementation, takes approximately 0.1 millis on a co-located Redis instance, microsecond latency at the infrastructure level. Rate-limiting overhead is negligible. Redis cluster scales linearly, 10 nodes shunch at 1,000 rate limit operations per second. At this scale, you're running infrastructure similar to Cloudflare's edge rate limiting layer, which enforces trillions of rate limit decisions per day. For DDoS context, a moderate DDoS attack might be 100 million requests per second. This is a network problem before it's an application problem. AWS Shield Advanced, Cloudflare, or Akamai Kona absorb this at the network edge. Your API gateway never sees it. Congratulations! You've completed the fundamentals phase of system design mastery. In the last 10 videos, you've built a complete vocabulary for system design. Scalability, load balancing, caching, databases, sharding, cap theorem, consistent hashing, message queues, and rate limiting. Starting with video 11, we apply all of this to design real systems. We'll design URL shorteners, WhatsApp, YouTube, Uber, and Google Search, the actual systems that appear in FAANG interviews. See you in video 11. Design a URL shortener. This video completes the fundamentals phase. 10 concepts, 10 videos. You now have the full vocabulary. Scalability, vertical versus horizontal, and when each breaks. Load balancing, algorithms, health checks, session affinity. Caching, where, what, and when to invalidate. Databases, SQL versus NoSQL, when each is correct. Sharding and replication, how databases scale beyond a single node. Cap theorem, the unavoidable trade-offs in distributed systems. Consistent hashing, how to route data without mass remapping. Message queues and event streaming, async decoupling, and fan-out at scale. And now, rate limiting and API gateways, protecting your system at the entry point. These are not 10 separate topics. They are a toolkit. You will combine them in every case study, starting with video 11. Video 11 is the URL shortener, the canonical system design interview question. We will apply the four-step framework, estimate scale from first principles, and build the architecture from scratch, using the concepts from all 10 fundamentals videos. It is a perfect integration of everything you have learned. See you in video 11.